And for the last part of today's lecture, I will talk about EMC measurement techniques. As a PCB developer and a project leader of electronic development, you will finally almost certain go to the EMC laboratory to measure electromagnetic compatibility. And to know about this measurement technique, it's good to be able to assist with the measurements and find some solutions if necessary if the electronics doesn't comply. Well, there are some measurement techniques you can also do in your lab in order to find out possible reasons for your device failure in EMC test lab, and then you can improve already in the lab, in your company or in your laboratory to be more certain that the next time the electronics would pass the test. So doing all these measurements in your own lab, it's much cheaper than booking a room, a semi-anechoic room in the lab, in the certified lab, and therefore that can save a lot of time and money. All right, so let me go now through these EMC measurements very briefly, just to get you acquainted with all the techniques that are available, at least the main ones. All right, so with the EMC measurements, we have three main topics. We are talking about environment in which we measure. For the immunity measurements, we need some sources, and for the emission measurement, EMC emission measurement, we have some receivers. And let's start with the environment. Usually what we do, we have some sort of a chamber that is shielded from outside, and also inside it has absorbing walls, so the electromagnetic noise coming from the device under test is not bouncing off the walls and actually gets absorbed anywhere. So this chamber actually acts as an infinite space. And what we usually have in this chamber, we have some sort of a device that we measure. It should be placed on some sort of a table which has to be non-conductive of a certain distance from the floor. I think it's 80 centimeters. And then we have the antenna at a certain distance. It could be 10 meters or 3 meters. And it could be also done in or outdoors. Here I'm showing the outdoor requirements. And the outdoor looks like the testing site looks like that. Nowadays in outdoors there are not many of such places left, because you can't find really space without any electromagnetic radiation. So it is more convenient now to measure indoors, and for that we have anechoic chambers, which actually mimic the outdoor setup, because all the walls are absorbing the EMC radiation, the electromagnetic noise, and these walls are made of metallic walls, which are then covered with tiles, and these tiles are made from ferrite material. So these walls are very good shielding against external noise which come from all the communication systems and other electronics. So the inside we only have the noise coming from the device under test. And usually floors are then covered with some absorbents that can be moved while the walls are fixed. And these white plates on the walls are actually just to protect the tips not to get mechanically damaged. So this is called anechoic chamber, because all of the walls are actually absorptive. We also have echoic chambers, which is the opposite. All the walls are reflective. So when you measure some noise from a device under test, in this case a motorbike, what you can see here is that we have some strange features in the corners of such a room, and the reason for that is that we get a standing wave in such a echoic chamber, standing electromagnetic wave. So we have some hills and some valleys of the signal, and we don't know where the antenna is. So we have some how to say, reflective parts which are trying to spread the noise, or they are moving and rotating all the time, and they are changing the pattern of that standing wave. So the valleys and hills are moving back and forth, and this antenna then measures some average value of the electric field. We also have semi-anechoic chambers, which are the most used, I would say, nowadays, because you have metallic floor and you have all the other walls and ceiling absorptive. So in these rooms, you can imagine you can walk and you can have very big rooms, even for the whole airplane. Now, maybe just a comment on at the beginning in this picture, why do we have test distance of 10 meters or 3 meters? Well, the reason is that such a test distance is needed because we are measuring electric field in the radiation pattern. We measure it out from 30 megahertz upwards. So at 30 megahertz, the near field ends at 1.6 meters. So from this point on, we have far field. Therefore, the measurement is done from 3 meters on to 10 meters. Okay. The GTEM cell is another option you can have in your company because it's so small that you can place it on a table. And inside this GTEM cell, you have an equipment under test, and the electric noise comes to the plate on top, and then it gets transferred to this connector here, and then you can measure it with the receiver. So a GTEM cell looks like that, and it's not a certified measurement equipment, but you can use it in your company, in your lab, because it's much cheaper than the semi-anechoic rooms. The anechoic or semi-anechoic rooms, they cost more than 500,000 euro, and this thing costs maybe a few 10,000. So it's much easier to afford it, and you can do some preliminary testing there, but you cannot do certified testing. We have different antennas for EMC measurements, and usually they are most commonly we use rod antennas like these semi-logarithmic to measure the electric field. Well, for antennas we have to know the antenna factor. The antenna factor is a factor that tells you the ratio between the voltage you get measured on the antenna terminal, and we can calculate the electric field out of it. So it tells you the ratio between those two, and this ratio is frequency dependent. So you have to insert that into your receiver in order to compensate for the antenna factor. In your lab, you can also do pre-compliance measurements very close to the device in the near field region. I would say the good point of that type of measurement is that you can measure very near, and you can exactly detect the source of your radiation by a very small probe. But you cannot do certified measurements with that because you don't know what would happen at 10 meter distance or 3 meters. Therefore, it is only used to compare the measurements before and after you change something on the circuit. And if you take your device into the lab and they show you that you're 10 decibels above the limit, then you can go in your lab, do some stuff on your electronics and try to lower the noise. And you can measure before and after. And if your change before and after is more than 10 dBs, you are quite sure that it could be that also in the chamber. You're not completely sure, but there is a chance that you can get better in the chamber as well, in the certified testing. And this is quite useful. So I will show you how we can do that in your lab. So what you have to have is either electric or magnetic field antenna. Remember, because you are measuring in near field, you have to care for electric field and for magnetic field separately. So measuring with this antenna, you will measure electric field. So what do you have? You have a coaxial cable with some tip that is sticking out, and this is how it looks like. So this coaxial cable has this middle wire sticking out of it, and here you have a capacitance then towards the noise source, towards the device under test. So this is then transferring electric field to the tip, and then it will be guided towards the oscilloscope or the spectrum analyzer. You can do it at home. You can also make magnetic field probes. And actually what you need is a loop, and then you use usually not just a loop you need, because the loop would also pick up electric field a little bit, and you have to pick up only magnetic because you can distinguish between those two. So you need a coaxial cable again, and you make a cut here. You can read all the details here in this diploma thesis of my student. So this is the ring you can make with the cut here, and you have to solder correctly so that you can then apply it to the spectrum analyzer. And you can actually measure the frequency range at which it is useful, and this is the result here. So you can use such detectors up to a few gigahertz if you want, depends on their size. The bigger the detector for magnetic field is, more it is sensitive because it takes more magnetic field, but you cannot use it to such high frequency. Maybe that one you can use up to a few 100 megahertz, while this one here can be used to this 2.4 giga. So these are different probes that we made, and this is for electric field and for magnetic. And by that you can test your device for electric field and magnetic field sources, and you detect the exact location of them. You can buy such probes also commercially, and you can use them. Of course, what you should do if you do a comparable measurement, you should always try to use the same way of measurement. You should place your probe exactly at the same position, and that's quite hard because you're doing it manually. So you can just move it for a few millimeters and you will get different results if you compare previous and after measurements. So it's better to have some sort of a defined instruments for that. And you have an option of using either a mechanical system like this one here, or you can use the scanner, which has a lot of sensors already incorporated in this plate, and then it has some sort of multiplexer to record these signals one after another. Alright, so these are both have advantages and disadvantages. That one can do a 3D scan because it will move one probe all over the PCB, and you can have really high resolution, but it will take time. That one doesn't need any spatial movements, so it has all the sensors already in place, but it can measure only at one distance, and the resolution is limited. So both have advantages and disadvantages. Mostly we are using this one. So actually, what we do, how we use it, there is a probe and we move it around the specimen, and there is a predefined coordinate system so that you can put your PCB exactly the same way after and before you change something. And yes, you can do also 3D scanning around the 3D objects, because you can import the 3D model of your circuit inside, and that's quite useful. So this is how the measurement looks like. There is an instrument, this is the XYZ moving table, and there is a spectrum analyzer. So this is how the results look like from a good circuit. You see only a few spots when the radiation is exiting the PCB, and when you measure in a semi-anechoic chamber at SIQ, for example, you see that this device actually passes the hardest test, CSPR 25 class 5. So that's quite promising. Well, that's another measurement you see of another very similarly made circuit with a little bit of a mistake. Just a few simple, very, very, very small features were changed, and this was the result. And you see a lot of noise all spread around the PCB, and there are some noise sources very hard. Here is where a big spike, and here. Now this is the result in the EMC lab, clearly not passing this test. So you can detect the spots here, and these spots are quite, I would say, devastating. So what can I say about these two circuits? Both these students that were made this circuit have passed also the exam here, but still they managed to make such a big difference. So the thing is in small details, and these small details can make your life easier or harder. And both were very good students. And here I can show you the result when I opened the shield here. So without the shield, you see how much noise comes from the inside electronics, because this box is the shielding box. So here we have the most radiative parts. And then you can do subtraction before and after. This is before opening the shield, and this is after. Because you have all the measurements defined, you can do subtraction between those two, and you see the result of a shield. So this is how much the shield itself is acting on your EMC footprint. So it's quite a useful device, quite a useful instrument, and we tend to use it quite often. We don't have it, we order it each time we borrow it from Amitech company. Okay, what about the receivers then? Well, regarding the receivers, we have two options. Either we have the EMC receiver or we have the spectrum analyzer. They are both very similar instruments. The only difference, or the big difference, is that EMI receiver is intended for EMC measurements, while the spectrum analyzer just analyzes spectrum of signal of any kind. So the EMI receiver is much more dedicated instrument, expensive, but you can just go there and select, I want this standard to be tested, and everything is set by itself. For the normal spectrum analyzer, you have to program everything by yourself. And also, it is much faster because it's intended for this type of measurements. And what is important, even if you use spectrum analyzer for EMI measurements, you can do it, but it will be much longer. It would take much longer. And you have to get careful that this spectrum analyzer also has the correct bandwidth, because the filter bandwidth is very important. Why is that? Because the standard says that, let's say if you have the signal that has these spectral lines, okay, and we are measuring them, and then you measure it with the very narrow bandwidth. So how the spectrum analyzer works anyway? So you have a filter, and that this filter in general is moved over the spectrum, and if the filter is narrow, then you would get a single peak here measurement, then here, 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 here. So that would be your result. If you have very wide bandwidth, so like that, then you will get only one point which will be much higher. Let's say it will be here, because actually what you are doing is you are taking all these spectral lines into account with the single filter, and you will get just a single point for that frequency. So using the correct filter is important, because otherwise your measurement will be completely wrong. And this spectrum analyzer that you are using should have this filter embedded. If not, then you cannot measure EMC. And EMI receiver, of course, have all that. What else? The next thing that is important is also the detector. So why is detector important? The thing is, what you can measure the average value of the electromagnetic noise, or you can measure the peak value. So let me go again to this drawing board here, and I can show you what type of signals you can have. Either you have very constant noise in time domain I'm drawing, or you can have noise that is bursting, then nothing, then bursting, then nothing, then bursting, and so on. So this noise is clearly, the upper noise is clearly has more power. So the average value and the peak value would be similar. If you go to this burst noise, you will have peak value really large and average value would be really low. So if you measure just average value, then you would not get much. But this noise is still acting on the other electronics, so you have to know the peak value as well. Therefore, we measure both. We measure peak value and we measure the average value. Now, the problem is that if your burst is just once in a time, let's say every 1 second, once, very short, then your peak value would be the same and the average would be almost zero. So, and if you have noise every second or every 100 milliseconds or every millisecond, that's a difference. Therefore, we need another detector. And there's another, the third type of detector is called quasi-peak detector. So detectors are like that. I would say average detector is a resistor and a capacitor. Peak detector is the diode and capacitor. And quasi-peak detector would be, the third one would be if you add the peak detector additional resistor here. So this would be quasi-peak detector. And that's how this picture shows actually. You see that we show average value if we have such a pulses, we have peak value, and we have quasi-peak value. Now, the quasi-peak value, the quasi-peak measurement takes very long time. So what we usually do? We usually measure average value and we measure peak value. And if peak value is below the limits, then we don't do anything else. If peak value is above the limits, then we measure the quasi-peak as well. And if quasi-peak is below the limits, then the measurement is passed. Now, this is how the measurement result looks like then. We have peak limits, we have average limits. And the peak limits are higher than the average by 10 decibels. And these are the results. These are, the blue are peak values, the green are average values. And these are peaks that are detected. And these peaks are all below the average and peak, and that's okay then. And here at 30 megahertz, the filter changes. And since the filter changes, you see the jump in your measurement results. Because if the filter changes its width, it can, as shown here, it can take more spectral components in one single measurement, so the power will be higher. So why do we change filter here? It's all written in standards, in which frequency range we need different filters. The thing is that changing the filter here is important because you cannot, if you have a narrow filter, then it will take forever your measurements, because here till 30 megahertz you have 30 megahertz to cover. Here from 30 to 108 you have 68 megahertz to cover. So to make it faster, the filter width is changed. Now, and finally, what kind of measurement is shown here? If you check here, you see that units are in dB microvolts. That means we are measuring conductive noise. Maybe you wonder, why do we measure until 108 megahertz, even though we said that the conductive noise is measured only up to 30 megahertz? Well, the answer for that is that this is measuring according to the automotive standard. And in automotive standard, conductive noise has to be measured up to 108 megahertz. And why is that? The reason for that is quite simple. If you think about it a little bit, it is quite simple, because here in this frequency range we have radio, FM radio. Now, conductive emissions are measured with in different way, but still they are measured in the anechoic room, because there you don't have any noise from outside, because that room is also shielding from outside noise. Therefore, it is useful to measure the conductive noise as well, although we are measuring it directly on the wires, right, on the tracks, on the connection lines. Okay, so the question is, how do we measure it? The thing here is you have to be a little bit careful, or at least I would like to show you what's the reason behind it. Well, here I can show you the typical connection. What we do have, we have a voltage source, and this voltage source is then connected to a device under test. This device under test generates noise that comes out of the device, this noise. So the voltage here is then measured. Well, the thing is, what is the voltage here? Well, if it is powered by ideal voltage source, then it would be ideally constant without noise. So we cannot measure, we would measure just the voltage of your source, not of the device under test. So we need some certain impedance, or let's say we have to use non-ideal sources. So instead of having ideal voltage source, we add non-ideal voltage sources which has some certain defined impedance. And then this noise would be transferred to noisy voltage as well. Now, these voltage sources that we use for such a purpose are called listen or line impedance stabilization network. Line impedance blah 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 stabilization network. Line impedance stabilization network. Yeah. Now, how do they look like? Here you see two of these listen circuits on this measurement table, which are then powered by a battery. These two are used for automotive measurements. But in general, we have listen circuits also for line power connection from mains power. Okay, so this is how listen looks like. And yeah. So this is the way the listen looks like. You connect it into mains power, and here you connect your device under test. So what is inside? Well, not much, I would say. A few filters. But what do we have? We have a source that is, let's say, a mains power source, an AC source. Now this already has some noise because you're plugging it into a wall plug. So that noise comes here and gets filtered because this coil has high impedance at high frequencies. That noise would actually be transferred here and it would be dissipated on the resistor because capacitor has low impedance. Now on the other side we connect device under test here, and this device under test is then transferring its noise into this circuit, and it would be again blocked by this big coil which represent high impedance at high frequencies, and it would rather be transferred through this capacitor back to this connector which goes to the EMI receiver. And here we have resistor which defines the impedance of 50 ohms. And for a device under test that has at least line and neutral connector, you need two of such listen interfaces. 1, 2. And these components, these values are predefined in standard, and every listen has the same. So what else can you have? You can have absorbing clamps, which are then clamped upon the cable, and you can then measure the electromagnetic field that is radiated by the cable and then transferred to a receiver. So this is an example of conductive emission measurements as I shown before. What you can do at home? Well, at home you can also make conductive noise measurements. If you don't have a listen circuit, you can actually make your own. It's not so hard to make such a circuit, a few coils, but they have to be of high quality. So this coil here, for example, should be an air coil without a core, so that it is the highest quality coil you can get. But maybe for low power supply currents, because the power supply current, actually DC current flows through this coil, it has to be big for very big consumers. But for small devices, you can make a small coil and then you can make your own listen circuit. What else? Well, you can also get some sort of ferrite bead, yeah, and you can put your one of the two lines through it, and then you put around a coaxial cable. So when this current flows in this direction here, it will actually generate magnetic field in that direction, and it would be picked up by this coaxial cable. And by that you can measure noise, differential noise. And here you see, for example, two measurements without some changes in the circuit before and after, and from that you can deduce how much you improved your circuit. What about immunity? With immunity measurements, you have two fields of, let's say, immunity: radiation and conduction immunity. Radiation noise comes through the air and conduction comes from the cables again. And in radiation immunity, you have radiation fields, electrostatic discharge, low frequency magnetic fields. And in conduction, you have different transients and supply voltage phenomena. Let me go through it a little bit just to acquaint you with it. Radiative RF coupling is actually reciprocal, yeah. So it acts both ways the same, mostly. So if you have a device that is very low in EMC radiation, it would be also very efficient, or let's say it would be very, it would have high immunity. It would be very immune from the external radiation. So it comes both ways. Making a good device in terms of EMC, it would act both ways, mostly. But sometimes, if you have a metallic case, there is a possibility that the standing wave is formed inside, because from outside the noise can couple through the cables, and then it can go inside through the cable, and then it would act as a radiator inside, and you can form a standing wave because the sheet is, or the case is metallic. So at a certain frequency you would get standing wave, and then you would have a big hill of that wave at a certain position, and that would maybe cause problems. So sometimes it's not totally the same. Anyway, what is possible to do? Fast transient bursts are first type of conductive noise, if you go now to the conductive noise, and these are very, very narrow pulses which are very large in terms of voltage, but they don't carry much energy. They just carry a lot of voltage. So these are very narrow and large pulses. As you see, they are 5 nanosecond and 50 nanosecond rise times and fall times. But you can have several of them, and you can have bursts of these trains of that bursts of signals. And depends where you are working on. You can have industrial, business, domestic, or lab environment. And in domestic, you have 0.6 of such transient bursts per hour. In industrial, you have 17. Now, when do they happen? When you turn on and off the light, some motors or relays or lamps, bulbs, and so on. Or indirect lightning strikes as well. Well, these fast transient bursts are dealt differently than these here. I will show you next the surge pulses, which are completely different. But fast transient bursts are mainly dealt with the voltage suppressing diodes. And they are generated by some high voltage source, which is then charging a capacitor, and then you have a switch or a spark gap, which then transfers this energy to the output circuit. And here you have some shaping circuit that makes a correct shape of that pulse. So such a device is then also used to power so-called capacitive clamps. Sometimes your noise has to be coupled to the cable via capacitive clamps, which is shown here. Or sometimes it can be coupled directly, like here, when you have direct capacitors coupled to the mains three-phase power lines, and these are then injecting these high voltage pulses, and the device is tested. Surge pulse is another type of pulse which has much more energy. So if fast transient pulse was very narrow and high, the surge pulse is much longer and maybe lower also in terms of energy, in terms of voltage, sorry. So at the end, what you have is much bigger energy, and this energy has to be dissipated somewhere in the circuit, and for that we use varistors and such high energy shielding components. And these surge pulses are also generated, but much more rare, let's say lightning strikes, direct lightning strikes, and if fuse blows, or some motor or high power switch is turned on or off. And in residential AC power socket, you have at least 3 of such 6 kilovolt pulses per year. And each time if your TV goes, then you have a problem. So you need some sort of surge protection devices. So, this can be bought in stores, and even, of course, they are also installed in TV sets and other house apparatus. Also, surge is similarly like transient bursts is generated by a high voltage source that is charging the capacitor, and then this capacitor is discharged into a shaping circuit. And again, you have different ways how to insert this pulse into a mains power. For example, you have such a device that it can insert this pulse at different times during the sinusoidal wave. This is all defined in standards as well. Finally, I would like to talk about electrostatic discharge. And this electrostatic discharge is human caused usually. So humans when we walk, we build up charge, and depends on the air, humidity, the type, the footwear that we wear, the clothes we wear, the ground we walk on, all that depends how much voltage you gain. And these pulses are also defined and are very, very, very sharp, very short, but have high voltages. And the voltage of these pulses depends on the relative humidity and the materials, and can be positive or negative. So wearing cotton is neutral. Wearing cotton is very good in terms of electrostatic discharge and high relative humidity, but not just that. So usually in factories they have special floors that have a certain resistance, so that your charge is then taken to the ground, and you have to wear special footwear for that, and you need to have a bracelet when you're working with electronic devices. Now, the problem is that in these manufacturing facilities, if you don't wear that, if you don't keep strict to the rules, you can get fired, because the electronics you're handling, if it receives electrostatic discharge pulse, it might still work, but not for a long time. Maybe it would work for 5 years instead of 10 years, or 1 year instead of 10 years. So that's a problem. So you have to be really strict with these rules. So even if we are as visitors coming to such a factory from time to time with students, they all have to wear some stripes on the foot with around an ankle that is discharging them to the floor. And everybody, when they enter this room, they have to go to the test facility and test themselves before they enter, because they have to measure their resistance. If the resistance is too low, then it's dangerous for you, because you can get killed. If it's too high, then it's dangerous because of the ESD. So you have to have a certain resistance value which is just in between. And I'm talking still about mega ohms, not kilo ohms or tera ohms. And in electrostatic discharge, you can have primary discharge paths, which means that you have a discharge and there is a current that flows to the ground. The shape of the discharge pulse is like that. Now, this is the spark, and this is then the conduction of the current. Now, if the current is conducted through a certain part of your case, for example, or even close to your device under test, you still generate electromagnetic field, which is just then coupled into the device. Of course, you can also get discharged into the case of the device itself. And if the case is metallic, then you have a current flowing through that metallic case to the ground, and then this electromagnetic pulse is then transferred to the circuit again. But you can also get discharged directly into the circuit. For example, if you discharge into a connector, or you can discharge into a display, and if the display has very thin foil on top, the spark can jump over to the display circuit itself, and that's quite often. You also have a secondary discharge path, which means that you discharge into a case, and then the current which flows through the case causes such a voltage jump that another discharge is happening here to the electronics, and then it is transferred through the cabling. So all that is possible, and for all these, measurements, we have special instruments called ESD guns. These guns actually are containing high voltage sources and some capacitor and resistors. So this is a human body model. Let's say that we as humans have around 150 picofarads of capacitance towards ground, and the resistance of the skin on the end of the finger altogether with the human body itself is 330 ohms. And that is then forming a human body model. And then you discharge into a tip. And this tip has a size of a human finger. And actually what you do, you stick that human finger anywhere on the device under test when you can. You stick it to the connectors, to the keys, to every opening in this, whenever you can. To connectors is the most harmful, I would say, to display and so on. And if the device stops working, that's failure. If it resets and doesn't start again, it's a failure. If it resets and starts again in a few seconds and the function is retained, then it's not a failure, or it is a failure, depends on the type of device. If it's life critical supporting device, then it should not fail in no circumstances. So yeah, it depends on the type of device. Even you can just charge the gun and just take it closer, and this high electric field would already start influencing your circuit. Or if you discharge. So you can discharge or not, both tests are done, and sometimes you have problem with it. Now, discharging looks like that. That's a guy who likes to try things. You might already seen him on YouTube. So this is how the discharging looks like. As I said, you can discharge in the housing or not. Depends what type of test you're making. Just bringing the gun closer to device without the discharge has already can cause a reset of the microcontroller, for example. Okay, continuing, you can make your ESD gun at home. You just take your cigarette lighter or a lighter for a domestic cooker for gas cooking, and you can ground it on one side and you can make a nice ESD gun, which is very powerful. I must say it's even more powerful than most of the guns you can buy. And if your circuit survives that, then you are, I would say, on the safe side. And finally, other immunity issues are also measured. I'm just showing them here. Low frequency magnetic field special coils are used for that, and different supply voltage phenomena can be tested as well. And for that, we have special signal generators. So to finish, what I wanted to show you with this lecture is mainly to show you different measurement methods. So you should be able to list and explain the most commonly used measurement methods and what they are used for. And you should recognize the measurement when I show you a picture of that. Like if I show you what is listen circuit, you should be aware that this is for measuring conductive noise and how it is made in general. And if I show you a picture of listen circuit, you should be able to recognize what that is. That's it. I wouldn't really go into details here because the measurements are usually done with others, but also you can, a lot of electrical engineers are employed in such laboratories doing measurements only. So if you get such a chance, it's a nice thing to do, because I think that they have a lot of business, and that's good. And here are some links where I took the pictures from to show you these instruments. Okay, so that's it from my side, and I hope that you enjoyed it. I think that each electrical engineer that is producing and developing new electronics will sooner or later come to such a lab, and it's nice to know how the measurements are in principle done.